Right, so today we're going to do stable and unstable nuclei, which is 3.2.1.2 of AQA A-level physics. Now this looks at the strong force and alpha and beta decay, which is kind of like remnants from GCSE. So the strong force is the force that explains why the nucleus is held together. It doesn't really make sense when you think about it. The nucleus consists of a load of positive protons. Why doesn't the electrostatic force repel them together? Well, the answer is there's a force that's stronger than the electrostatic repulsion, and that's called the strong force. Now, strong force is weird because unlike other forces, whether it's attractive or repulsive depends on distance. A lot of forces, they go as 1 over r squared, so the force decreases with distance, which is fine, but the strong force is a slightly strange one. If you are very close to something, the strong force is repulsive. And by very close, I mean 0 to 0.5 femtometers. A femtometer is 1.5 times 10 to minus 15 meters, so incredibly tiny. You're talking about distances similar to the radius of the nucleons. Nucleons being protons and neutrons in the nucleus. Now, these strong forces are all felt by nucleons, which are hadrons, right? So all these particles that feel the strong force are hadrons. The particles that don't feel the strong force, they're called leptons. But that's another video. Now, if you're very close together, very close, you're repelled by the strong force, which is helpful, prevents the nucleons from colliding close together. But between 0.5 and 3 femtometers, the strong force is attractive, and this is what holds the nucleus together despite the electrostatic repulsion that the protons feel. Beyond 3 femtometers, however, the strong force doesn't exist. It just goes to 0. So it's repulsive between 0 and 0.5 femtometers, attractive 0.5 to 3 femtometers, 0 after 3 femtometers. And 1 femtometer is 1 times 10 to minus 15 meters. I've seen in some questions those kind of like answers change. You might see if you do past paper questions, it's kind of like, from 0 to 5. These values here are the ones that AQA are currently kind of like the most recent past papers quote. Now, regardless of this, some nuclei can be unstable, right? And the instability of nuclei and the reasons why is a kind of year 13 topic in nuclear physics. But in general, it's to do with the number of protons and neutrons and then the overall size of the nucleus. Because actually, if the nucleus gets larger than 3 femtometers, it's going to be unstable because the strong force can no longer hold the nucleons together. And in general, the number of protons and neutrons kind of want it to be equal. That makes the most stable nucleus. But that, again, is dealt with in year 13. There are loads of ways nucleuses can decay. There are 2 ways that are covered in this spec point. The first is alpha decay. It's exactly the same as GCSE physics. Alpha decay is the emission of 2 protons and 2 neutrons from the nucleus. In general, a nucleus that has a really large mass, a really large nucleus, will undergo alpha decay to produce a smaller, more stable element. So the equations look like this. The atomic number, the mass number, and then the proton number. Mass number decreases by 4, proton number decreases by 2, and it produces 42He. Sometimes see this as written 42 alpha instead of He. That's fine too. They just changed the GCSE spec to bring it to 42He to represent a helium nucleus. Beta decay, there are 2 types of beta decay. Beta minus decay is the one that we learnt at GCSE. So beta minus decay is actually neutron decay because protons are the only stable baryons. So of the particles that feel the strong force, protons are the only ones that are stable. So neutrons decay into protons, but a neutron decays into a proton plus an electron. That's what we did at GCSE. At A-level, we bring in the fact that actually it also produces an electron antineutrino. You might know it needs to produce the electron antineutrino in order to conserve lepton number. However, that's not how we discovered about the neutrinos. Neutrinos are massless and chargeless, so they basically don't interact with anything. I find them terrifying. Electrons and positrons, though, so when they looked at beta minus decay, they noticed that these electrons were released with a range of energy. So didn't make sense, violated the law of conservation of energy. Every time the neutron decayed into a proton, the proton remains in the nucleus and the electron is fired out. But these electrons shouldn't have a range of energy, so there must have been something else being produced to take away the remaining kinetic energy. So the electron antineutrino was hypothesized in order to conserve energy. So for beta minus decay, the you're gaining a proton. So the atomic number, the proton number goes up by 1. Mass number stays the same because the neutron's turning into a proton. And then you're also producing an electron, and this is the symbol for an electron. Sometimes you see this again as 0 - 1 beta to represent beta decay, but this is what they do now in GCSE. Plus 0 anti-electron neutrino. Beta plus decay is kind of like the undoing of beta minus decay. So a beta plus is a proton turning into a neutron plus a positron plus an electron neutrino. So I kind of think it's like the opposite particles for each one. There's also another thing called electron capture, which is sort of like the undoing of beta minus decay, but we'll do that one later. It's a different spec point. So beta plus decay is a new one. You don't do this at GCSE, and beta plus decay is where a positron is produced. Again, positrons are produced with a range of kinetic energies, so something else must have been produced as well, and in this case it was a electron neutrino. So for beta plus decay, the mass number stays the same because the proton's just turning into a neutron, so it's the same number of nucleons in total, but the atomic number goes down by 1, so because you're losing a proton, right? So all these three produce different elements and also radioactive, also particles. That's it.